Good evening, viewers, and my dear students who are watching this program. My teacher, the live classroom, which is the biggest classroom in the UAE. Today it's a special session for you. For those who are preparing for exams, we'll have a revision on the a few chapters at the beginning of the course. Grade 12 physics will focus now. However, if you have any questions from even grade 11 or grade 10, if you have anything to ask, you can very well call us and ask your doubts. You can anyway, now those who are watching this program, remember this is a live show, it's a live classroom. You can take your notebook, you can take a pencil, pen, be ready to solve some of the questions which are coming in the first few chapters of physics grade 12. As I mentioned at the beginning, even if we are focusing grade 12, if any questions you have related to 12, 11 or even 10th grade, if you have anything to ask, definitely you can feel free to call in this number which is displayed on the screen. You can watch it on the screen, you can see it on the screen, you can note down the number, you can call us and tell us what exactly the doubt is. We will be able to sort it out. Okay, as I always mention, it is your program, your classroom. Feel free to converse. We will have an interactive session through this program. Okay, anyway, today we are solving some of the questions relevant to physics grade 12. You can, those who are not there at home, parents, please make a note on this. This is some questions which are to be solved from the first few chapters of grade 12 physics, and even its repeat show is going to be there tomorrow morning 7 o'clock. But this is now this particular slot, that is 5 to 6 today, is a time for live session. Take your textbook and see if you have any questions to solve and tell us. You can definitely, you can either call in this number or you can SMS or you can send the mail ID, whatever is the way you, let's see. Anyway, first let's focus a few questions. Straight away we'll move on to the, but when we go through the questions, you may be very clear about it. Always I used to mention about this one, when we go through questions, not only that particular question, you have to see which concept it is related to and which content of which chapter, which section, and related areas as well. If it is the other way, if it is asked what can be the answer, you know, that way, all different ways you would be able to make it out. Okay, not only confining to that particular question. Correct. All right, now you can just see the first question. Have a look at the first question, all of you. See the first question. There a circuit is given. Look at the question carefully. A circuit is given with resistors. This chapter, this question is from the chapter current electricity. This is one of the questions taken from a board paper, and the currents given I1, I2, I3 and I4. Hope you have noted it down. You may draw this diagram to your notebook. Let us solve it together. Okay, the values of EMF, all the values are given. Now we can look at the board. Watch the board now. Yes. This resistance R1 is given as 4 ohms, R2 and R3 given as 15 ohms, each one 15 ohms, and the other resistor is 30 ohms. This is 30, R4 is 30 ohms. Clear? So that means, now what the question is, calculate the equivalent resistance of circuit and current in each resistor. Equivalent resistance of the circuit you are going to find. Very first thing, by seeing a circuit of this sort, sometimes you may be thinking about applying Kirchhoff's rules. But remember, Kirchhoff's rules are mostly applicable whenever more than one cell comes in different branches of the circuit. In different branches of the circuit, if more than a cell comes, then we can say we have to use Kirchhoff's laws. But here it's not, that is not required. Just first part is you have to calculate the equivalent resistance. Equivalent resistance. You see these three resistors we have. How do you find the equivalent resistance of the circuit? Very first thing is you have to find out, identify which all resistors in parallel or series. You can make out one thing, you know, these two resistors connected together and here there is nothing. So that means this all can be considered as connected together. Okay. So all the three ends are connected together to one end and the other three ends are connected together to the other end. That means these three resistors are in parallel. These three resistors in parallel. You know the parallel combination effective resistance, we have the equation 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is 1 by 15 plus 1 by 30 plus 1 by 15. Right. That means this would become what? 2 by 15 plus 1 by 30. Okay. It further means 30 is LCM, 30 by 15, 2 multiplied by 2 plus 1. So this is 5 divided by 30, that is 1 by 6. So 1 by 6, otherwise 6 ohms is the 1 by 6 is 1 by Rp. Therefore, effective resistance in parallel combination is 6 ohms. Is that clear? So we found out the effective resistance of this together is 6 ohms. Correct. But now this 6 is now as a whole you can consider connected in series with this. Right. So that is R1 is in series with the rest. That is 4 ohm is in series with the rest. So what is the total resistance over here is 6 ohms. So 6 plus 4. It's clear. So total effective resistance of the combination is 4 plus 6, that is 10 ohms. So one answer we got. Right. This is 10 ohms resistance as a whole. Next thing to understand is what else you got to find is the current through each branch. Okay, current through each branch we are going to find. How do you find the current through each branch? That is I1, I2, I3, I4, all the 4 currents we need to find. The very first thing is, you know, the effective resistance of the whole thing together is 10 ohms and parallel combinations effective resistance is 6 ohms, right? So 6 ohms is this much and this is 4 ohm. That's how together 10 ohm. So total resistance is 10 ohm, total voltage is 10 volt. So what will be the current? Current is total EMF by total resistance, that is 10 divided by 10. So 1 ampere is the total current. But you can make out one thing, this resistance R1 is in series with this. So what's the answer there? R1 is in series with this means whatever current delivered from the battery is what is passing through the resistance R1. That is total current, that is 1 ampere. 1 ampere is what is passing through this. So we got one answer, that is I1 is equal to 1 ampere. This current is 1 ampere. Clear? Now we are going to find out current through all the 3. I2, I3, I4 and right. I2, how do you find? We can make out one thing, at this point this 1 ampere will be divided among the 3 resistors. So one method we can adopt is, this resistance as a whole we know it is 6 ohms, right, and the current is 1 ampere. So what will be the total potential difference across this whole combination? PD is equal to current into resistance. Total current is 1 ampere. Resistance of this combination is 6 ohms. So we get 6 volt as the PD across this whole combination. 6 volt. So 6 volt is a PD in parallel combination. It means that 6 volt is what is the same across each resistor because they all are in parallel. So we can now find the current through each resistor. So what will be I2? I2 is 6 divided by this one, right? And how about I3? I3 is again 6 by 15 and I4 6 by 30. So what all answers? See, I2 is 6 total voltage divided by 15 ampere. I3 is how much? 6 by 15 again. I3 also the same thing. and I4 6 by 30. Okay, 6 by 30 amperes. Okay, so these are the currents and resistance values. Now I invite your attention again to the same question. You look at the question once again. Okay, see the question. Yeah, you could see now the question. There are 4 resistors connected and an EMF, and the question is calculate the equivalent resistance of the circuit and the current in each resistor. So we found out the equivalent resistance as 10 ohms, and the current you can make out. Again you see the board. We found out the total resistance here. We found out the total resistance of the parallel combination in series with this. Then you found out the total current, that is the current through this, then current through each resistor which is connected, which all are connected in parallel. So PD we found out, and PD is considered to be the same. All right. Now you look at the next question. So look at the question. You see in the question, calculate the current drawn from the battery in the given network. That's the question given. That is the network. You can make out from the diagram. There is a 1 ohm resistor, a 2 ohm resistor, 5 ohm, 4 ohm, 2 ohm. Okay. Then we have a battery. This battery voltage is 4 volt. Okay, so this is the diagram. The question is calculate current drawn from the battery in the given network. I hope it is clear. Now you look at the board. So we can make out one thing. This is, there are 5 resistors connected. I think you must be knowing about this concept. That is, basically what you are going to find out is what is the current drawn from the battery in the given network. Okay, so how do you make it out? This, whenever resistors of this sort comes, what you have to check is make sure if it is whether you will be able to make out as series parallel combinations or not. Is there any possibility of taking series or parallel? Series we can say only if both the ends are connected together and no other connection in between, right? But there is no such a connection here. Similarly, parallel means both the ends should be connected together, like this. So there is no any connection like that also. So neither series nor parallel combinations you will be able to make out using this diagram, right? And in this diagram we cannot make out series or parallel resistors. So what we should do is, next option is what? Try to make a Wheatstone's network. Wheatstone's principle we have to apply. Wheatstone's network is, normally we draw Wheatstone's network like this. Wheatstone's bridge, must be familiar with this, right? This name we normally write P, Q, R, S, and this is normally the place where the galvanometer is connected. So this arrangement of resistors is what is normally called Wheatstone's bridge, right? So now there is Wheatstone. This we can compare with that of a Wheatstone's bridge, right? So you look at this the diagram, and how do you compare it with this? See, P is over here. Here we have 1 ohm, right? And P, Q, this is 2 ohm. Okay, this is Q, this is P, and this is R, and we have S, and this is the resistance coming at the center, this one, right? This resistance over here is same as this. So what does that mean? So it can be, that is, this given diagram can also be considered as a Wheatstone's bridge. What is the next step? If you are able to make it out as a Wheatstone's bridge, the next step is what? You have to check if it is a balanced Wheatstone's bridge or not. Dear students, you can see how the final resistance we are able to make out. Balanced Wheatstone's bridge means this condition. What is the condition for balancing? P by Q should be equal to R by S. Is that condition balanced here, or is that condition satisfied here? P by Q, see, 1 by 2, and this is 2 by 4. So 1 by 2 is equal to 2 by 4. So ratio is the same. Ratio is the same means the bridge is balanced. If the bridge is balanced, what else we can make out? There is no current at all passing through the resistance over here. That is, there is no role for this resistance, or we can assume that part as an open part. That is simply we can take this out. This resistance is now taken out. Why? Because it is a balanced Wheatstone's bridge. If the resistance of this one is taken out, then it is easy for calculation, because look, 1 and 2 are in series, these two are in series. When these two are in series, 1 and 2 in series means what? Effective is 3, 1 plus 2, right? Similarly, 2 and 4 also in series, effective is 6. So, this is 6 ohm, 4 plus 2, 6 ohms, and this is 3 ohms. Now, what else you can say? 6 ohm and 3 ohm in parallel. We can redraw it like this. There is a 6 ohm resistance here, there is a 3 ohm resistance here. These two are connected in, or can be considered as connected in parallel. If they are connected in parallel, what will be the effective resistance? You know, RP, we have if two resistors there, we can even say R1 R2 divided by R1 plus R2, that is 6 into 3 divided by 6 plus 3. So, we get how much? 2 ohms. So, that is the total resistance of the combination is 2 ohms. If the total resistance is 2 ohms, how much will be the current drawn? The current I is equal to, total voltage is how much? 4 volt. 4 volt divided by 2 ohms. Total voltage divided by total resistance, which is 2 amperes. You know, we got the answer. How much is the current drawn from the battery? So, the current drawn from the battery is 2 amperes. I hope all of you got it clear. Once again, let me tell you about that. See, you are given a resistance network, and we are asked to calculate the effective resistance. So, first if any series path, that is a conventional way we do. If any series or parallel combinations available, take it out and reduce it, finally we will be able to get the final answer. Whereas, if we are not able to make out like that, what you should do? You should try to reduce it into the form of a Wheatstone's bridge. When the Wheatstone's bridge is balanced, that balancing condition you can apply. P by Q is equal to R by S, then we can solve it in this way easily. This is the easy way of solving this kind of a network and finding out the total current. Is that point clear, all of you? Okay. Now, as I mentioned at the beginning, you can work it out along with me, and if any confusions there, you can call us. Okay. Now, look at the next question. See the next question. Okay. Watch the next question on the screen. This is also a question asked in one of the board papers. Okay. See, there are two batteries, but it is specifically given we must use Kirchhoff's rules to apply to find out the values here. Kirchhoff's rules to be applied, but it is again asked as a it's a different type of question. It's not a normal type of question usually they ask. This is given, currents given, some resistances are given, some points are mentioned here. Okay, I think all of you have noted down the diagram, drew the diagram. Okay. Yes, now you look at the board. It's given the point A is to be a zero potential. That is, over here the potential at A is given as 0. Okay, if this is the case, calculate the potential at B. Potential at B is the question, and we will have to use Kirchhoff's rules. Potential at B. That means, the potential at B, I think B must be here. This is B. Potential at B we are going to find. Yes. Okay. So, how to find the potential at B? I will tell you an easy way. This current is given as 1 ampere. Okay. This is given as 2 ampere. And what will be here, therefore, by using junction rule, Kirchhoff's junction rule, you can say current through this would be how much? 1 ampere. Because look, 2 ampere is entering the point D and leaving is 1 ampere. Therefore, as current entering should be equal to current leaving. So, 2 ampere is entering, 1 ampere is leaving, therefore, 1 ampere should leave this way. Okay, now while applying Kirchhoff's rules for finding out the total potential difference between 2 points A and B, we have to find out the potential difference between, or we can find the potential difference between A and B using Kirchhoff's rules. Okay, how you will do that? For which, what you should do is, you can choose any paths you can go. This way you can go, this way, or this, any path you can go. But which one is to be taken appropriately? Wherever the quantities are known. You see, this resistance value is not given, it is R. So if you go this way, you will not be able to reach the answer properly. Why? Because this is unknown. So, and this way if you go, then you see R1 is unknown. So better way is what? A, C, D, B, like this you can go. Here all the values are known. Is the point clear? Alright, now again this is positive terminal and this negative terminal, you may draw the direction of the EMF this way, and even here the direction of EMF you can draw like this. So we need the, suppose you are finding the potential difference between A and B. Potential difference between A and B means VAB we are going to find using or applying the concept of Kirchhoff's rules. You start from here. See what you first observe, the negative, the EMF like this 1 volt, right? And arrow is opposite, no, in opposite to the direction in which you are going. So it should be what? -1, -1, correct? And then this one is what? Potential difference 2 multiplied by 1, 2 into 1, right? And to here also the arrow is opposite, so negative. So negative 2 into 1, okay? Again going this way, here there is a positive 2 plus 2. This is the potential difference between A and B. There is no other resistors on the way. It means we can write it as -1, -2 plus 2. This would be -1, right? So VAB is -1. VAB you can further write as what? VA minus VB, potential difference. But it's given in the question VA is 0. So 0 minus VB is equal to -1. Therefore, what is VB? Potential at B is 1 volt. If you understood, it's a simple question, but you have to carefully approach it. Okay, so look at the question once again. The question is, this diagram is given. Okay, sorry, not this question. You can have a look at the board. What you saw now is the next question. We'll do that, but coming to this, see, this is the diagram given in the question, and this question is to find out what's the potential at B, but what you are given is the potential at A as 0. And these current values are given. If values of currents given, what else we can make out? The 2 ampere current is coming over here, and it is distributed into 2, like that it is coming, right? And we followed a path which is or through which we are able to get known values, right? So like this is, you see this path you are following and getting, adding all the potential differences and EMFs, and together we are getting potential difference between A and B, that, and of which potential at A is substituted as 0. So we are getting the value of potential at B. I hope it is clear. Okay, so now one more question. Let's see, have a look at the next question. Look at the next question. A circular coil of N turns and radius R carries a current I. This is a question from magnetism, right? As I mentioned at the beginning, it is we are seeing the questions from the first 5 chapters of the textbook. Circular coil of N turns and radius R carries a current I. It is unwound and rewound to make another coil of radius R by 2, current I remaining the same. Calculate the ratio of magnetic moments of the new coil and the original coil. Ratio of magnetic moments. Okay, so the first thing, now I'll explain it. Listen. The first thing is, what's the equation for dipole moment of the circular coil carrying current? Equation for dipole moment of a circular coil carrying current, you can find M is equal to, what's the expression? Okay, now you can look at the board. M is equal to IA. This is the expression for magnetic dipole moment, right? But over here the first coil, when we say it has got N turns. N turns means the total dipole moment will be NIA. So first we will write M1 is equal to N turns there, current is I. How about area? Area is pi R squared. This is the dipole moment initially, right? Now the new dipole moment you will find. What is done is over here it is unwound and rewound to make another coil of radius r by 2. Right. So the new radius becomes, so M2 is equal to, but by the way we can make out how many turns are there. Right. The new number of turns you can find. What is given is it is unwound and rewound to make a new coil. That means total length is remaining the same. That is total circumference will remain the same. N into 2 pi r is the total length of the wire. That would be the total length again. So number of turns now, let us say N2, total number of turns N2 into 2 pi, what will be the radius r by 2. Okay. So here if you make out like that, therefore N2 we can write S becomes 2n. N2 is 2n, right. So that is over here M2 would be the number of turns is what, 2n into current is the same, and how about what is say radius r by 2 squared. Okay. So M2 is equal to, what you get here is 2 ni pi r squared, but r squared by 4 it will come, 1 2 will be cancelled. So what will be the answer? N I pi r squared by 2. So what the question now is, we are going to find out the ratio of magnetic moments of new coil and the original coil. So new coil and the original coil, that is M1 by M2 is how much? That is what you will find, M1 by M2. When you divide the equation 1 by equation 2, what do we get? We get 2 by 1. That is the answer required is 2:1. If you understood? So what was the question? There was a coil having carrying current I, having number of turns N, radius r. Dipole moment is this much. Now that coil is unwound and then rewound to make a new coil of radius r by 2. So radius becomes r by 2, but simultaneously what happens? The number of turns therefore doubles. Correct? Then you get the dipole moment of that as well. N number of turns is 2n, I, then area, new area. We get dipole moment M2 in the second case, then ratio we are getting. Right? This is the answer, M1 by M2. Okay, so now the picture is we are in the process, those who are watching this class late, we can make out one thing. Today we are dealing with the questions based on physics grade 12 at the beginning chapters or chapters, the first few chapters. Take out the questions, these questions which we are discussing, you take it out, okay, and still go through these questions again and try practicing more and more. And now I am going for a short break. After the break, when we come back, we will solve more questions, and if you have any doubts again, that also can be sorted out. All right, and anyway, stay tuned. We will be back after a very short break.